Welcome to the video on similar polygons. First, let's review what we said it meant for two figures to be similar. We say that two figures are similar when they have the same shape, but not necessarily the same size. Because they have the same shape, all of their corresponding angles have to be congruent. But because they're not necessarily the same size, while corresponding sides have to be in proportion, they don't necessarily have to be congruent. The symbol that we're going to use to represent the word similarity is one that we're taking from our congruent statement. We're taking that little squiggle symbol, and anytime we see that little squiggle symbol, it's understood that that means similar. So in this first example, when I say ABCD is similar to figure EFGH, I know that they have pairs of corresponding angles that are congruent and pairs of corresponding sides that are in proportion. Just like when we write a congruency statement, it's important to match up all the pairs of congruent parts. The same is true when we write a similarity statement. So because of the way these guys are written, I know that angle A in the first polygon corresponds to and is congruent to angle E in the second polygon. So angle A is congruent to angle E. Likewise, I know that angle B matches up with and is congruent to angle F. And if I continue in a similar fashion, I know that angles C and G correspond and are congruent. And then lastly, I know that angles D and H correspond and are congruent. And while my pairs of corresponding sides are not necessarily congruent, I do know that they are in proportion. That is, if I compare the length of AB to its corresponding side, EF, and I compare that ratio to the next pair of corresponding sides, BC and FG, I know those two ratios are exactly the same. And likewise, it's going to be the same ratio that I get when I compare DC to its corresponding side, HG, and then the last pair of corresponding sides, AD and EH. Notice that as I've written each ratio here, I've always compared the longest polygon to its corresponding side and the smaller polygon. And it's important that when you write your ratios, you're consistent. If you put the side from the large polygon in the numerator of the ratio each time, it's important that you be consistent as you go along and put the smaller polygon or the corresponding side of the smaller polygon in the denominator of the ratio. So again, that consistency is something that we've talked about before, and it continues to be important moving forward. We say that two polygons are congruent only when all the lengths of corresponding sides are in proportion. The ratio between the lengths of the corresponding sides is called the scale factor, which you've seen that word before, or the constant of proportionality, which is a new word that you haven't seen. But constant of proportionality just means scale factor. We can use the scale factor or the constant of proportionality in order to solve some problems that involve similar figures. Now down in example 2, they're giving us this picture of these two right triangles, and they're asking us to determine whether or not they're similar. We will know they're similar if the lengths of all the corresponding sides are in proportion or have the same ratio or scale factor. So when they ask us for similar here, what they're really asking us is, are the lengths of the sides proportional? And I should say corresponding sides. So I'm going to go ahead and find out. In order to do this, I need to figure out which is the smallest pair of sides, which is the smallest side of the larger triangle, and which is the smallest side of the smaller triangle. Well, if I look at the larger triangle, triangle NLH, I know 2 out of the 3 sides, but I don't know the third. I also know that this is a right triangle, and because it's a right triangle, I can use the Pythagorean theorem to find my third side. So 9 squared plus 12 squared is going to equal the square of the hypotenuse. So I now know that my hypotenuse in the larger triangle is 15. I'm going to go do the same thing for the smaller triangle. Hopefully by now you know if the one leg is 3 and the other leg is 4, then to make that Pythagorean triple, the third side has to be 5. If you didn't know, you could go ahead and just do the Pythagorean theorem again for that smaller triangle. So now I'm going to go ahead and compare. And when I compare, again, it's important that I compare corresponding sides. So when I look at the smallest side of the first triangle, that's going to be side NL in the larger triangle. I have to compare that to the smallest side in the second triangle. So my comparison, or my ratio, is going to be 9:3. And I want to see if that comparison is the same as the comparison that I get when I do the other two pairs of sides. So the second longest side in the first triangle is 12. I need to compare that to the second longest side in the second triangle, 4. And then my last comparison I need to make between the longest side of each triangle. So I want to compare 15 in the first triangle to 5 in the second triangle. And I'm asking myself, are all three of those ratios equal? Well, every single one of those will simplify down to 3/1, which means they are equal. So yes, these two triangles are similar. And now I need to find the scale factor, or the constant of proportionality. I'm usually going to work small to large, so I'm going to ask myself, what number do I have to multiply 5 by to obtain its corresponding side in the larger polygon? Well, 3. So the scale factor here is 3. I found my scale factor by going from small to large. If you had found the scale factor of 1/3 because you compared or started with the large one and went to the smaller one, that would be correct as well. On a quiz or a test, they'll always ask or tell you whether they want you to compare the small one to the large one or the large one to the small one. Okay, moving along. Number 3 says the sides of a quadrilateral have those lengths. Find all of the lengths of the sides of a larger polygon that's similar if the constant of proportionality, or in other words, the scale factor, is 2:5. I'm going to go ahead and start by drawing a picture. A quadrilateral I know has 4 sides. My picture isn't a very good picture, but it'll be good enough to get the job done. I want to label those 4 sides 8, 10, 12, and 15. The second polygon is larger, so this is my larger of the two. And they want me to find the lengths of all 4 of its sides if the constant of proportionality is 2:5. So this is my larger one. This is my smaller guy. I'm going to go ahead and write some comparisons. I want to compare 8 to its corresponding side using that constant of proportionality. So 8 over its corresponding side in the larger polygon, I'm going to call x. And my constant of proportionality in moving from one to the other is 2:5. Since I put the smaller side, or the smaller polygon in the numerator, I need to use that smaller number from my constant of proportionality in the numerator. Larger value goes in the denominator. Now I can just multiply. 2x is equal to 40. Each x is equal to 20. So the length of the corresponding side in the second polygon is going to be 20. Now I'm going to go ahead and compare these two sides. So 10 is to y. And again, I did smaller over larger. So in my constant of proportionality, smaller over larger. So 2y is equal to 50, making each y value equal to 25. And therefore, the length of the corresponding side in the larger polygon is 25. You could find the last 2 sides in a similar fashion, but in the interest of time, I'm going to go ahead and move on to the next and last example. All right, example 4 talks about a triangle. We couldn't have a good video here without at least talking about one triangle. So I'm going to say, or start with triangle hat. I'm going to label all my dimensions in my picture. So H to A is 9, A to T is 15, T to H, 18. They tell us that this triangle hat is similar to this triangle pin. So I'm going to go ahead and draw a triangle PIN. I know that H will correspond with vertex P, A will correspond with vertex I, T will correspond with vertex N. They also tell us that the distance between points P and I is 12. They want us to find the other two sides of the triangle. Again, in the interest of time, I'm going to do just one of the two sides. I would do the second one in a similar fashion. I'm going to compare a pair of corresponding sides. So I'll write the ratio is 9:12. And I know that the second pair of corresponding sides have to be in that same ratio. So 18 is to x. And again, when I wrote my ratio, I did the smaller polygon over the larger polygon. You may write the ratio any way you like as long as you're consistent. So now I'm just going to go ahead and cross multiply. And when I solve for side PN, I find that the distance between points N and P is 24. All right, I'm going to have you flip over to the top of the next page. I want you to identify what the important understandings and the key ideas are from this video that you'll think you need to remember for a quiz or a test, and then use what you've learned to solve the following problems. We'll check your answers when you come back to class, make sure we're all on the same page and where we need to be, and then we'll be able to progress and take this idea forward and on to the next level.